John from Byte Basics here, and by watching this video you're going to learn what a number system is, what a base is in relation to a number system, and why number systems are important, especially to programmers. If I asked you to write down how many sweets you could see, you'd most likely write down 11 like this. This representation of the number 11 is the number system you've probably been using all your life and is called decimal or denary. However, if you saw 11 written down like this, you'd likely know this also represents the number 11. This is another number system called tally. There are other number systems you may be less familiar with though, for example binary and hexadecimal. In binary you represent the number 11 as 1011 and in hexadecimal B. Each of these number systems has what's known as a base. So for decimal the base is 10, binary 2 and hexadecimal 16. So a number system is simply a way of representing numbers or quantities. As you've seen, we can represent the same number or quantity in different ways using different number systems. So I just said that decimal, the number system we normally use, is a base 10 number system. But what does that actually mean? We're going to use the number 137 to look at this. Let's split 137 into single digit columns. You'll find I do this a lot while talking about different number systems. Each of these columns has a value, and in the case of decimal those are ones, tens and hundreds. When we multiply the digit in a column by the value of that column and then add the results, we get the number. So in this case 1 times 100 gives us 100, 3 times 10 gives us 30 and 7 times 1 gives us 7. Add 100, 30 and 7 and we get 137. So what does this have to do with decimal being a base 10 number system? Let's think about what the valid single digits are that we can have in each column. In this case we can have 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. That's a total of 10 different digits, and this is because decimal is a base 10 number system. Now let's think about the values of the columns. The first, ones, is equal to 10 to the power 0. The second, tens, is equal to 10 to the power 1. And the third, the 100s, is equal to 10 to the power 2. And the next column would be thousands, which is equal to 10 to the power 3. So each column has an increasing power of 10, which is again due to decimal being a base 10 number system. So the base of a number system defines two things. Firstly, the number of different single digits you can have in a single column. That number is equal to the base, like we saw in decimal, where we can have one of a possible 10 digits in each column, as decimal is a base 10 number system. Normally, these values are from 0 to the base minus 1, like with decimal where we have 0 to 10 minus 1, which is 0 to 9. Secondly, the values of the column are increasing power of the base, starting with the base to the power 0. Let's use those two rules to learn about binary, which is a base 2 number system. As it's base 2, we can only have one of a possible 2 digits in each column. Those digits are 0 and 1. Also, the columns have values of increasing power of 2. So instead of ones, tens, hundreds like we had in decimal, we have 2 to the 0 which is ones, 2 to the 1 which is 2s, 2 to the 2 which is 4s, 2 to the 3 which is 8s, 2 to the 4 which is 16s, 2 to the 5 which is 32s, 2 to the 6 which is 64s, and 2 to the 7 which is 128. So 137 is represented as 10001001 in binary. To see this we can do exactly the same as I did in decimal and work across the columns, multiplying the values above the columns by the digits below and then adding together those results. So we have 1 times 128 which is 128, 0 times 64 which is 0, 0 times 32 which is 0, 0 times 16 which is 0, 1 times 8 which is 8, 0 times 4 which is 0, 0 times 2 which is 0 and 1 times 1 which is 1. When we add 128, 8 and 1 we get 137. I'll be releasing a full video on converting between binary and decimal and back very soon. Once you know a number system's base, you can tell by looking at a given number if it's valid for that number system. For example, if we have 120 written down, we know this isn't a binary number. Why? Because if we split the number into columns, we have a 2 in one of those columns, and as binary is a base 2 number system, we can only have 0 or 1 in each column. However, if we have the number 101, this could either be decimal or binary, as if we split it into columns, we only have the values 0 and 1 in each column, which is valid for both decimal and binary. Without additional information, it's impossible to know which number system is being used. To combat this, the base or number system in use is often written down next to the number. Hexadecimal is a base 16 number system, so using the previous two rules we talked about, we know the column values are increasing powers of 16. The first three columns would have the values of 16 to the 0, which is 1s, 16 to the 1, which is 16s, and 16 to the 2, which is 256s. Using the other rule, we know each column can have one of a possible 16 values. Those values are 0 to the base minus 1, which is 15 in this case. This begs the question, how do you represent the values of 10 to 15 in a single digit column? The way this is done is using the letters A to F. So decimal 10 is represented with an A in hexadecimal, 11 a B, 12 a C, 13 a D, 14 an E, and 15 an F. So you can have numbers like E5B in hexadecimal, which is 3675 in decimal. To see this, we do exactly the same as we did with decimal and binary, and work our way across the columns, multiplying the value at the top by the digit below and adding the results together. We have E lots of 256, and remember E is just 14, so 14 times 256, which is 3584, 5 lots of 16, which is 80, and B lots of 1s, and B is 11, so 11. When we add 3584 plus 80 plus 11, we get 3675. Again, in some cases it can be impossible to know what base a number is if it isn't written down. For example, 101 is a valid binary, decimal, and hexadecimal number. It would represent the number 5 in binary, 101 in decimal, and 257 in hexadecimal. 22 is both a valid decimal or hexadecimal number, but not binary. And A4 would only be a valid hexadecimal number, but not decimal or binary. There are many other number systems, but the three I've mentioned in this video are some of the most common. You may be wondering why you would want to know number systems other than decimal. Well, both binary and hexadecimal, but in particular binary, are important to know if you're trying to understand or program a computer. Anything you store on a computer or compute will be done in a binary form. So take a sentence you write in Word, for example. It will be converted to a binary representation before it can be stored. Even things like a photo must be converted into a binary representation before they can be stored. This is done because the storage in a computer has two states, on and off. I think of it like an LED. On can be represented as 1 and off as a 0. So you can think of binary numbers, for example 101001110, being stored like this. You might think this is all very low level, and when you use a computer you don't need to know this, but it can have some odd effects if you're a programmer. Here's a quick example of that. It's a really short bit of Java code. Don't worry if you can't program, you should still be able to understand this. So ignore everything except lines 4 and 5. So on line 4, we simply print the number 21474836647, and if we look at the output, it's printed as you would expect. Now on line 5, we print 21474836647 plus 1. Now the output I intuitively expect is 21474836648. But what actually gets printed is negative 21474836648. This unexpected behaviour is caused by the way that the number is being stored in binary form. Now exactly why this happens is a bit out of scope for this video, but don't worry, I'll go into those full details in a future video. Hexadecimal is used in a number of places relating to computing. One place you may have come across it is when defining colours. If we look at the colour picker in Photoshop, we can see a hexadecimal representation of this colour. It's often used as a concise way to represent large binary numbers, as every 4 binary digits can be represented with a single hexadecimal digit. So a long number like 101111010101 can be represented as BD5 in hexadecimal. So that's been a very brief look at a few number systems. Don't worry if at this point you're still a bit confused. I'm going to be making videos focused on converting between the different number systems I've mentioned and how to do mathematical operations in binary. The next video will be on how to convert from binary to decimal. Please subscribe so you're alerted when that comes out. There's a link to some practice questions in the description if you'd like to go back over some of the stuff in this video. Please, as this is my first video, leave a comment with some feedback or a question, and thank you for watching. I hope to see you in future videos.